All right, so welcome everyone to the ICTS Colloquium. It's a pleasure to have Apoorva Khare from ISC Maths Department today giving the talk. So as you all know, Apoorva is an associate professor in the Maths Department. He's also a member of the Analysis and Probability Research Group. He joined ISC in 2017. And he's got a wide range of interests, as you probably can tell from his abstract and a good sense of humor, as you can tell from his title, Moments in Positivity. So I'll leave it to you now, Apoorva. Please take over.
Yeah. Thank you again for the very kind introduction. So so I'll hope to tell you about positivity, which is one of the one of my major research interests, and how it connects to a lot of different other areas. And yeah, let's just begin without further ado. Some of it is based on joint works with various co-authors, and yeah, I'll get that. I'll mention them as well. Oops. Yeah, so just to begin, I will begin with some kind of a working example and a definition. So a real symmetric matrix. So all matrices in this talk are real, and I think all of them are symmetric as well. Such a matrix is positive semi-definite if all the eigenvalues are non-negative. That's one way to define such a matrix. The traditional definition is that the quadratic form of this matrix induced by this matrix is positive semi-definite, meaning this condition holds for all vectors U. Right? Clearly, they are equivalent. One can show this. So, for example, here are two such matrices. These are correlation as well. So, correlation means that the diagonals are all the diagonal entries are 1, and these matrices are positive semi-definite. As you can see, the entries are non-negative, in fact, and there are some zeros here, right? And so on in the other one as well. And the pattern of zeros is according to what we you can encode these patterns of zeros by graphs. I will do so later in the talk. But this is roughly the graph, which is a path graph, because every node, so 1, 2, 3, 4, 5, 1 is connected to node 2, but not to 3, 4, 5. 2 is connected to node 1 and node 3, and so on. Okay, simple question is raise every entry to the same fixed power alpha, for which alpha are the resulting matrices positive. I mean positive semi-definite. So it's a very simple question, and we will answer this question in the course of this talk. And because of this graph here, you'll see this is a nice connection to combinatorics. So this is just some kind of a motivating or working example. I will get back to this. So let's begin now with one of maybe the first connection of positivity that I can tell you about to analysis. So yeah, the notion of positivity, of course, has been around for, shall we say, hundreds of years. So maybe one of the earliest settings you can think about, I mean, positivity in analysis. Positive real numbers have been around for a long time. Where in analysis, for example, the second derivative test shows up in calculus, and that has when you have a positive definite Hessian matrix, you have a local minimum. Right? So that's one very, very early instance. But anyway, more in other areas of analysis, if you will, here are some examples. There are Toeplitz matrices which come from measures on the torus, on the circle, in fact, and Hankel matrices which come from measures on the line. There are totally positive matrices and kernels, as I said. A very distinguished class of such kernels are the Polya frequency functions. You can also have kernels on Z cross Z. Z is the integers. That's Polya frequency sequences, Hilbert space kernels, and so on. Okay. And of course, maybe the first one is the sort of most ubiquitous in today's big data era. You see positive semi-definite matrices all over applications because of correlation and covariance matrices. And so one natural question to try and study is to understand what operations preserve these notions of positivity, not just matrices, but kernels and so on and so forth. Right? And this question has been studied in various settings for quite a long time now. And so let me start with so I'll focus on the matrix theory question in this talk. And so to set some notation, let Pn of I, so n is an integer, I is a domain. Pn of I is going to denote the n by n positive matrices whose entries lie in I. Right? So not the eigenvalues. Often people prefer the spectrum to lie in some specified subset, but I want the entries. And suppose Pn, when I don't tell I mean Pn of R, let's say. So given a function from the domain to R, when is it true that if you act on a positive semi-definite matrix, A is positive semi-definite, when is it true that the entry-wise action of A, of F on A is positive semi-definite? So normally, maybe you might have seen this thing about, acting by acting on the spectrum. So diagonalize the matrix, act on the spectrum, put it back together. But now I just want to literally act on the entries, nothing more. So it's very simple. When does it preserve positivity? And so clearly, obviously, fx equals x preserves positivity because you don't change the positive matrix. Fx equals 1 works because you would get the matrix of all ones. And that matrix of all ones you can easily check as eigenvalues. Most eigenvalues are 0 and one eigenvalue is n. So these eigenvalues are non-negative. So the question is, what other functions work? And so the answer is that, so this has a long history, and to tell you the answer, let me first tell you the fundamental result in this setting. This is by Schur, and it's curious because I know Schur when I was doing my PhD is in representation theory, so I know Schur is an algebraist, but Schur has a ton of contributions in analysis, and this is, for example, one of them. So the Hadamard product or the Schur product or the Entrywise product of two matrices, and these need not be square, they can be over any field or ring. So it's just the product you tell undergraduates to never do. Right? So like first year calculus students, do not multiply matrices in this way. So it's just entry-wise multiplication. And the theorem that Schur proved in 1911 is that if A and B are positive matrices, then so is their Schur product. And why is this useful in answering the question? Because if I take B equals A, then what you see is if A is a positive matrix, then so is A Schur A. But A Schur A is literally just Aij squared, which means that you're applying the function x squared to a matrix and preserving positivity. So that's the reason why this Schur product theorem answers the question, provides one answer. Now you can put B equals A dot A, and so you would get A dot A dot A. So then you would get that x cubed also satisfies this, x fourth. And by induction, every integer works, preserves positivity on Pn for all sizes and all powers. And again, this is not some new observation. This was done by Polya and Zigo in their book on problems in analysis in 1925. So these are all very old observations. Now, if you have two matrices which are positive, then it's easy to see because this U transpose AU is positive, U transpose BU is positive, then U transpose A plus B times U is positive. So sums and similarly positive multiples of positive semi-definite matrices have the same property. Right? So as a result, if A square is positive and 2A cube is positive, then A square plus 2A cube is positive. And more generally, if all these monomials preserve positivity, then every polynomial with non-negative coefficients does the same. And the other thing you can see easily is that the set of positive matrices is closed under pointwise limits. So if you have a sequence of matrices which are all positive, they converge to a given matrix, then the limiting matrix is also positive. And as a result, if you know that such polynomials preserve positivity, then their limits, which are convergent power series, will also do the same. And so as a result, if you take any power series with non-negative coefficients, then that answers the above question. Now, this was, again, as I said, Polya and Zigo in 1925, so it's still very early days. And they ask in their book, or I think they do, I should really check, are there any other functions? But it's anyway a natural question. These are a huge class of functions that work. Are there any others? And if so, what others? Turns out the answer is no. So it's a very nice and happy ending to the story. These are the only functions that work. And so this was proved by Schoenberg, who in fact also named Polya frequency functions after Polya. But that's, as I said, a subject for another day. So Schoenberg proved in 1942, so 17 years later, that there are no other continuous functions that work. And 17 more years later, Walter Rudin proved that there are no other functions. You don't even need to assume continuity. And so this is their theorem. Suppose just for simplicity or for one version, take I goes from -1 to 1, a function from I to R with no restrictions, no assumptions. The following are equivalent. The function applied entry-wise preserves positivity for all matrices A in all dimensions n. If and only if the function is exactly of the above form. It's a convergent power series. The coefficients are non-negative. So these functions are first of all said to be absolutely monotonic. That's just a name. That was this class of functions was studied by Bernstein a long time ago. So let me now tell you about some motivations. Where was Rudin coming from? Where is Schoenberg coming from? So Rudin was motivated by harmonic analysis, Fourier analysis. He's written a famous book on locally compact groups, so it's not surprising. And circle S1, he studied preservers of positive definite sequences. So these are just sequences of real numbers, but by infinite. So they go in both directions. And if you look at the Toeplitz matrix, then that is positive semi-definite. So meaning all the principal minors are non-negative. By the way, if you heard what I was saying before the start of the talk, if instead of principal minors you take any minors, then that's exactly what is called the Polya frequency sequence. So the notion was sort of there. I mean, some simpler version of the notion was already there in Rudin's thing. Of course, Polya frequency sequences were done a few years before Rudin's work. Okay, so there's all at the same time, the early 1950s and the late 1950s. So in his 1959 paper then, going back to these positive semi-definite sequences, F preserves positive definite sequences or Toeplitz matrices of all sizes if and only if F is of that power series form. So remember, the theorem that Schoenberg and Rudin proved is that it preserves positivity on all matrices of all sizes. But Rudin said you don't even need all matrices. You just need the Toeplitz matrices, which are positive semi-definite of all sizes. And not just only the Toeplitz matrices, you in fact need Toeplitz matrices of rank at most 3. That's a far smaller set than the set of all positive semi-definite matrices. Just rank at most 3. Okay? So that's what he means here. So these Toeplitz matrices arise as, or these sequences arise as Fourier coefficients of non-negative or positive measures on the torus, on the circle. And 3-point supports, measures with 3-point supports give rise to the rank being 3 or less. So this is what, so that the size of the support of the measure directly correlates to the rank of the matrix or the bi-infinite matrix. Yeah? So that's what Rudin showed, which means that you only need to work with matrices, preservers of positivity on rank 3 Toeplitz matrices of all sizes are automatically power series with positive coefficients. It's a far smaller set than Schoenberg's original work. And in parallel to Rudin, you can talk about a different locally compact group, the real line. And on that you have things like probability measures, of which you have moments. Right? So if you take the same question, and so you say instead of looking at sequences of Fourier coefficients and which functions preserve them, meaning Toeplitz matrices, I can look at sequences of measures and which functions preserve those, or take a measure sequence to another measure sequence. And so that's what we call moment sequences. And so given a positive measure, with moment sequences given in this way, the expectation of x to the k against the measure, one can ask the same question that Rudin studied for this locally compact abelian group. So take some measure, and for which functions take the kth coefficient sequence for all k of the measure mu to the measure sigma for some different positive measure of the line. And that was what we worked out recently, so in the parallel result to Rudin, but it seems to be as sort of simple to state and very, very similar as well. So this is Rudin's result. Given a function from I to R, let's say I is -1, 1 or minus infinity, infinity, or any symmetric domain in between, F acting entry-wise preserves the set of positive definite sequences, if and only if preserves Toeplitz positivity on the Toeplitz matrices, but rank at most 3, as I said, if and only if it is exactly of that form. So that's what, so the first two are sort of, there are classical results by Khare, Theodori and others. By the first two are if and only if. And the third one clearly implies 1 and 2, but they have to imply 3. That's the hard part. Right? And in exact parallel to this result, here is the Hankel analog of this. So consider the set of moment sequences, which are moments of measures on the line, on the real line. F preserves the set of such moment sequences if and only if it preserves positivity on Hankel matrices of all sizes, but again the rank is at most 3, if and only if the function has the same form. So it's still this same absolutely monotonic analytic form with convergent power series of non-negative coefficients. Right? So that's and 3 implies 1 and 2 in both cases are very simple. It's really the 2 implies 3 assertions that are difficult. And yeah, and we also actually have a multivariate version of this. And again, the answer is the same, that for preserving positivity on tuples of moment sequences, you must have a power series representation with non-negative coefficients. So it's a very robust condition. Okay. So these two results then greatly weaken the hypotheses. You don't need to work with all matrices of all sizes, of all ranks, just the positive ones of rank less equals 3 and even structured ones. Now, there's one more characterization of such matrices. Positive matrices are gram matrices, meaning you can choose certain number of vectors, and these matrices are just the entries of these matrices are the set of inner products of these vectors. So if the matrices have rank at most 3, then they can all be recovered from inner products of vectors in a 3-dimensional, 4-dimensional, or any higher dimensional space. And so what Rudin really was showing is that if you take a Hilbert space of dimension at most 3, dimension at least 3, and that preserves positivity on gram matrices, then F must be a power series with non-negative coefficients. Now, why am I telling you this result? Because such functions, there's a name for these functions in modern day mathematics or in applied maths and so on, in related areas. These are called the positive semi-definite kernels on the Hilbert space, and they are important, it seems. I'm not an expert in machine learning via these reproducing kernel Hilbert spaces. Alan Pinkus, among others, has worked on these things. Plenty of other people now. This is a very fashionable topic. So, but the moral of the story is that in 1959, Rudin had already classified the positive semi-definite kernels on R3. And that is relevant in machine learning, except that in 1959, there was no machine learning. So anyway, now of course, with the same conclusion can be drawn from our Hankel result. But so yes, sometimes these applications really do take decades to show up, in other places. And if Rudin's application took 50 years to show up, Schoenberg's paper application took even longer to show up. So now let me tell you what Schoenberg was doing, and then lead into what that application is. So Schoenberg was actually working on metric geometry. So meaning metric spaces and maps between them and so on. So now we go, instead of coming forward in time, we go backwards in time, and we ask, how did the study of these, how did Schoenberg come to his theorem? What was he doing to answer this theorem? And that comes from the area of distance geometry. So as all old stories should start, once upon a time there was a metric space, and that showed up in, say, the early 1900s and so on. Well-known people worked on it. Now, of course, it's ubiquitous everywhere. But here is a sample result from 1910 by Fréchet. If X is a metric space with n+1 points, it embeds into Rn, except not with the Euclidean metric, but with the sup norm. Fine. So it's very natural then to ask, okay, these are Euclidean spaces, but with non-Euclidean metrics. Can you embed X into a Euclidean space with the Euclidean metric? When does it look like the real world, if you will? Right? And so that question was studied by various people. Menger in 1931, Fréchet a few years later. Schoenberg, so I want to tell you how Schoenberg got to this result of his on preservers. He started by understanding Fréchet's result, and so in the very next article in the same volume of the Annals, Schoenberg proved the following result, and he reformulated metric space embedding using matrix positivity. So fix a finite metric space with n+1 points, as I said. Then this so remember, all the data of this metric space is embedded in the distance function, right? Or in other words, in the distance matrix, which is an n+1 by n+1 matrix. So X isometrically embeds, meaning with the preserving distances in some Euclidean space Rm, if and only if the n by n matrix, so not n+1 by n+1, remember, this is the n by n matrix, whose ijth entry is the distance from x0 to xi squared plus this minus this. So there's some entry. If and only if this matrix is positive semi-definite. So a metric space, so distance matrices are never positive semi-definite because their diagonals are 0 and their off diagonals are positive. So even a 2 by 2 has a negative principal minor, and that contradicts the eigenvalues being non-negative. Right? So, and so on. Anyway, so the point is, distance.
Question. Where's the m in this? Where's the dimension of the space?
N is
little m.
I will tell you about m in a second. So it embeds into some Rm. That's all I'm saying.
Okay.
There exists an m such that this embeds into it if and only if this matrix is positive semi-definite. That was his first part, and there's a part remaining. This line is blank. It's not going to be. Schoenberg actually understood which is the smallest m. So clearly, for example, an equilateral triangle cannot embed into the real line, because how can you embed 3 points which are at equal distances from each other on the line? But it does embed in R2. So similarly, you can ask, okay, here is a finite metric space. What is the smallest dimension in which it embeds? And that smallest dimension M is given precisely by the rank of this matrix. So that's your M. Yeah, so any M bigger than the rank of this matrix will work. But yeah, so this is the smallest step. So this is what Schoenberg used, how he obtained a connection between metric geometry and matrix positivity. And actually, one implication is not hard at all. Actually, one implication is that if X does embed, if these are actually inner products of x0 minus xi bracket x0 minus xi, and then you expand out the Hilbert space inner products or the Euclidean inner products, norm square x0 minus xi, this matrix turns out to be the Gram matrix of something. And that is why it's positive semi-definite, because all Gram matrices are positive semi-definite. So one implication is not hard, the other is not too hard. I'll just leave it at that. Okay, so that's one thing. Now Schoenberg, as I said, so first of all, he was understood which metric spaces embed into a Euclidean space. But then he wanted to go further. I want to embed now metric spaces into a Euclidean sphere. So, like a one-dimensional circle in 2 dimensions, the 2-dimensional sphere in R3, and so on. So every sphere, SR-1, let's say, and in particular, the Hilbert sphere is just, you take each sphere is like R3, the sphere is x1 squared plus x2 squared plus x3 squared equals 1. In R4, it will be plus x4 squared equals 1, and so on. So you just take their union, and you get square summable sequences, right? Summation xi square is equal to 1, and that is the unit length vectors in L2. And that's really what is the Hilbert sphere, except in Schoenberg's time, they called it the Hilbert sphere. So every sphere has a rotation invariant distance, and therefore, so does the Hilbert sphere. Namely, the idea is the following. So let's see, I've given 2 points on the Hilbert sphere or on a sphere. And by taking limits, you can take them on the Hilbert sphere. Anyway, so imagine a sphere, I have 2 points. If those 2 points are negatives of each other, x and minus x, then the distance is said to be pi. The angle is pi, the distance is pi. If they're not negatives, then these 2 points and the origin are not collinear. So there's a unique 2-dimensional plane in R infinity even, or any Rn, that passes through these 3 points. Slice the sphere, the n-dimensional sphere, in that plane. That's the intersection of a plane with a sphere. And if you have read Flatland, then you know that the intersection of a plane with a sphere is a circle. Well, so that's the great circle because it contains the origin. So it's a great circle. And now x, y are points on this great circle. Therefore, now the distance is very clear. It's just the angle between them, the smaller of the 2 angles between them. Or in other words, the arc cosine of the inner product. Right? That's the definition of the angle by Cauchy-Schwarz. So now applying cosine entry-wise to any distance matrix, therefore, what would it give you? It would precisely give you the cosine. It would give you the angles. Sorry, it would give you the cosine of the angles, which is the inner products. And these are Gram matrices, so they're positive definite, positive semi-definite. And that's the definition of a positive definite function. So a function is positive definite on an inner product space, on a metric space, if applying the function entry-wise, now you're seeing the entry-wise calculus come in, yields a positive semi-definite matrix, even though the original matrix you applied it to was a distance matrix and never positive semi-definite. So Schoenberg, what he did was he classified all the continuous functions for which f composed cosine is positive definite. And so he said f composed cosine is PD on the unit sphere and finite dimension if and only if f is a positive combination of Gegenbauer polynomials or Chebyshev polynomials. And so, right? So these are these ultraspherical polynomials of a given dimension. So that was Schoenberg's original result in that same paper, which I was mentioning about. But now here is the connection to matrix positivity preservers. So it's any Gram matrices of vectors in a sphere. Well, remember, the Gram matrices are precisely the inner products. So what is the diagonal entry of such a thing? It's the xi norm square. Since xi is on the unit sphere, the diagonal entries are 1. And so Gram matrices are just these. And so these are the same as correlation matrices, and the rank is bounded above because the vectors come from a sphere. So f composed cosine, which Schoenberg was studying, is positive definite on the sphere if and only if applied to any metric distance matrix, it gives you a positive matrix. But the definition of cos of distance is just the inner product. So applied to any gram matrix, it gives you a positive matrix. But all gram matrices have these. So applied to any correlation matrix, the function preserves positivity. And that's how Schoenberg came to his theorem. He's looking really, his theorem really translates to understanding functions preserving positivity on correlation matrices of all dimensions. But rank is less equals R, because the dimension of the sphere governs the rank of the matrix. And if instead now this R was taken to go to infinity, if the rank was unbounded, then you would get Schoenberg's theorem. Because then you would be working with positivity preservers on all correlation matrices and so on. Now, 70 years later, not just 50 years maybe like Rudin, but 70 years later, this subject has now renewed interest because of this impact in high-dimensional covariance estimation, which is where I'm getting to. And indeed, Schoenberg did make the leap from finite dimensional spheres to the infinite sphere. And so he said that f composed with cosine is positive definite on the Hilbert sphere, which is, remember, unit vectors in L2. If and only if that function has to look like, it's the intersection of all the Gegenbauer families. And so it has to look of this form. But cosine, remember, when theta goes between minus theta goes between 0 and pi, cosine is 1 to 1 and on to. It's a bijection to this interval. And so it's really, when you write down x instead of cos theta, you really see that this is exactly Schoenberg's theorem that we started with. The only preservers of positivity are precisely power series with positive coefficients. So that's how Schoenberg got to this theorem. While looking really at correlation matrices, I think machine learning may not have been available then, but correlation matrices were. Anyway, but he was really looking at them. And so that's going to come up in the next part of the talk then. And so for more information, let me refer you to a survey that we wrote that tells you about results of Schoenberg and Schoenberg with von Neumann and various other people working on distance geometry. Okay? So all that can be found in the survey. So it's broken up into two parts, but the unified complete survey is on the archive. Okay, so now let's move on to correlation matrices. So this is why it's renewed important. So actually, I started looking at this subject when I was working in Stanford in my previous job. And I was there working with a faculty in statistics. And he was interested in this modern application of Schoenberg kind of results. And that's how I got into this area. But then we discovered all these old connections of Schur and Schoenberg and various Rudin and various other people. But so let me quickly tell you about this part. Again, I'm not an expert in statistics, so I'll just briefly gloss over it. But yeah, one of the major challenges in all kinds of applied fields is to detect structure, to detect dependencies. And nowadays, data is huge. You have hundreds of thousands of variables, and you want to detect structure in these dependencies, in these variables. The simplest dependency is the linear one, and that's captured by correlation or covariance, right? So for example, I'm given some kind of a data, I'm given p many random variables, and I'm given n many samples of random vectors, each of them, is p-dimensional. From this data, I want to estimate the underlying true covariance matrix. And when we learned it in school, at least, the number of variables were very small, the number of samples were very large, life was very good. Nowadays, there are, as I said, hundreds or thousands or even more random variables, which makes collecting data itself expensive. Storing and working with it is computationally expensive. And so this is a hard problem because now you have few samples and many variables. And so in modern day settings, therefore, if you look at the covariance matrix, this is either n or n minus 1, depending on whatever unbiasedness. You look at this matrix, each summand is a rank 1 matrix. So the whole thing is rank at most n, and as I said right now, the number of samples n is quite small compared to the number of random variables. So dimension is big, rank is small, so these are very singular, highly singular. Also, they may not have any kind of sparsity in their structure. They may not be zeros because when you take measurements, it's noisy. But of course, you might expect from your model that many random variables are independent or conditionally independent, and so you should expect to see lots of zeros, and you don't. So that's why these kind of matrices require some form of regularization. You have to clean up the matrix or improve the properties. And of course, the resulting matrix, whatever you do to regularize it, what you get at the end must be in the parameter space. It must be positive semidefinite because it serves as a proxy for the actual covariance matrix. Right? or for the sample one. So either way, you need it to be positive semi-definite. So here is one concrete sort of area. As I said, this is in fact the area in which my collaborator at Stanford, now he has moved himself to Davis, was very interested, graphical models. So let x1 through xp be a collection of random variables. So for example, I'm measuring temperature at points on the Earth. And maybe I have 10,000 marker points where I measure the temperature in an attempt to do some kind of climate reconstruction or something. So it's conceivable that if you measure the temperature in Alaska, then it might depend on the temperature in Russia, but not for the temperature in say Australia or Antarctica. Right? Certainly, you might be reasonably forgiven for assuming that if you condition the temperature on the neighboring points, then it's independent of the rest of the globe. So it's very it's expected, maybe it's rare that all xj's depend strongly on each other, and in fact you expect most things to be conditionally independent. And therefore not using prediction, it reduces the dimension of the problem, and that's a nice thing. It translates, it helps you compute faster, predict faster. Now these independencies, conditional or otherwise, translate to zeros in these covariance matrices. And so there has the traditional modern approach, if you will, which has been state of the art for quite a few years now, is to use kind of compressed sensing method. Right? You want to get sparse estimates. Those are like L0 kind of penalties, but that's not a complex problem. So you impose L1 penalties, you use convex optimization, some kind of compressed sensing methods. Famous people have worked on these things. And these have proved to be very successful, especially for dimensions up to a few thousand. In modern day data, like gene-gene interaction to detect kind of rare diseases, in paleoclimate reconstruction and so on, sometimes you have 10,000 variables, 50,000 variables, even more. And then these things start slowing down. It's computationally quite expensive. So one interesting alternative, promising even maybe, is to do the following, is to regularize by thresholding. And the idea is very simple. Suppose this is my true covariance matrix, sigma, and S is my sample. And you see that these two entries are very, very small compared to the other ones. So you might again be reasonable in assuming that these were just measurement errors, this was just noise, and these should actually be zero in the true covariance matrix. Okay? And it's natural to threshold. That's what it's being called. This is called hard thresholding. You don't change the other entries, you set these to zero. Okay? And so this is a nice fun exercise in looking at numbers, but this is very significant. If say you have a 100,000 by 100,000 matrix and only 1% of the true entries are non-zero, then you really can clean up this matrix using say hard thresholding or maybe soft thresholding or other similar kind of regularizations. So more generally, you can apply some function to every single entry of the matrix. And so this is what we are doing. The previous slide applied the function where you don't touch the entry if it's bigger in modulus than certain threshold. Otherwise, you make it the entry zero if it's small enough. So that's what is called hard thresholding. In general, applying such functions to sort of help improve the properties of the sample matrix is regularization. And this is clearly now there is no optimization here. There are no recursive algorithms or anything. It's just directly apply the function to the entries of the matrix. This is very scalable. And the regularized matrix is further used in applications. But the point is here, what you need to critically assume or ensure is that whatever this matrix you get out of it has to stay positive semi-definite because it's being used as a proxy of the true covariance matrix. And the problem is you can't just apply any function arbitrarily, f of every entry, and expect the answer to stay positive semi-definite. So really, that's really the key question now. Is when does this kind of a function preserve positivity? And that's how we came to this question in the beginning. And then, of course, we looked at the literature and discovered a lot of classical mathematics and experts in analysis had worked on the same question throughout for decades, basically. Okay, so now let me come then to one more difference between Schoenberg's result and Rudin's result and application-based questions or motivations. Schoenberg's result characterized functions preserving positivity for matrices of all sizes. Right? All dimensions, the rank may be constrained, but the dimensions were allowed to grow in spheres and of just all ranks in all dimensions anyways. But it's okay. Lots of people have studied such problems, and here's a list of more people that have been studying them throughout the ages, throughout the 20th century. But okay, so here is the next natural mathematical variant. Okay, I know the answer when I try to preserve positivity in all dimensions. What if I fix a dimension? That's a very natural refinement, but it's very key in applications where you know the dimension of a problem. I know how many random variables I have. So why should I talk about functions acting on bigger size matrices? I know exactly what I want to get. And then also, why should I work with only power series with positive coefficients? In fact, such functions, when you apply them to a matrix, they will never induce sparsity. You will never get zeros if you apply them to positive numbers, right? So it's unnecessarily restricted to work with such functions or to work in all dimensions. Now, so it's natural to ask which functions preserve positivity without these last three words here. So remove these three words, right? Just for all a in Pn for a fixed n, which functions preserve positivity? So 1 by 1 and 2 by 2 are easy, they are known. In fact, Harkrishan Vasudeva in 1979 answered the question for 2 by 2. It's not very difficult, that's the only characterization. Let's say if you restrict to matrices with positive entries. For 3 by 3, what about 3 by 3? 3 by 3 is still open. So this is a very challenging problem. Even for 3 by 3 matrices, we do not know which function, all the functions which preserve positivity in a fixed dimension. I'll get to exactly how challenging in 1 minute. So yeah, in the next slide to this one. So what we have been doing in the recent few years is to revisit this problem with modern applications in mind. And it's very nice that these applications provide very nice refinements of the original problem and motivate various kind of, and actually connect to a lot of different areas. So you can ask about, if I know how many samples I have, usually, as I said, you can't collect too many samples when you have a 1 lakh by 1 lakh matrix to make. So maybe your samples are only 5 or 7 or 10. And then when you have that, the samples directly give you rank constraints on the covariance matrix. So it's very natural to ask which functions preserve positivity on rank constraint matrices. People like Alan Pinkus have looked at this. These are sort of well-known matrix theorists. And we also looked at them recently. You can ask about when you have zeros in your matrix at determined positions. As in my original slide, there were zeros. You can talk about moment sequences and Hankel or Toeplitz sequences. You can ask about general functions. These are when you restrict sort of matrices to rank or sparsity or structural constraints. You can restrict functions to only ask which polynomials preserve positivity in a fixed dimension. Which power functions preserve positivity in a fixed dimension. That was the original slide again. Right? And then there are all kinds of applications which I will probably skip over. Well, the symmetric function theory I will skip over today. But let me just outline two broad areas that I will skip over then. So one is Polya frequency functions and sequences. And this is fascinating, beautiful history. Sorry. Question,
Avinash. You go back 2 slides. So you said so here, for example, for n-grade. So if you just considered thresholding functions, go to the nearest integer or something like that, the positive definiteness is not known even for such restricted class of functions?
For thresholding functions, it is known, yes, for sure. I mean, so again, I'm only looking at, so it can't really go to the nearest integer because covariance matrices will not stay positive semidefinite. Not correlation matrices will not, even 2 by 2 will not stay positive semidefinite with threshold that. So for example,
thresholding that go to 0 if it's less than some threshold or something like that. So those functions are known to preserve.
Importance of thresholding, these properties are known. The preservers kind of things are known.
And that's all n, I guess.
Sorry, and what was the
Thanks.
Yeah, okay, great. In fact,
no, I said it's for all n as well. Yeah.
So for certain individual specific families of functions like power functions or thresholding functions, much more is known. And in fact, those results are actually used in an application. In very, very applied papers as well, which I haven't really read, but I know of them and where they have been used, some papers. Okay, so so two areas which I will then skip today are Polya frequency functions and sequences, and also, as I said, connections to algebraic combinatorics, to Schur polynomials, and so on. I will tell you one result from here in the following setting. So as I said, we don't know all functions which preserve positivity when applied entry-wise on 3 by 3 matrices. Fine. But can we restrict to some special families? For example, can we restrict to power series or to polynomials? So remember, Schoenberg's theorem said that the only functions that work in all dimensions are power series with positive coefficients. So clearly, if you ask to preserve positivity only in dimension 3, in a fixed dimension, then you are asking for far fewer constraints, requirements. So you should expect far many more functions to work. a larger class of answers since you have fewer constraints. So in particular, since all power series with all positive coefficients work, you should expect to find power series with negative coefficients, at least one negative coefficient, and one power series with such coefficients that works on Pn for a fixed n. Remarkably, this was not known until 4 years back. So that was sort of surprising, and so this was something that we now understand. So what was known is the following. Suppose I look at matrices with just positive entries, or even a smaller class of matrices. I restrict my matrices, I restrict my things to functions. So, and suppose I have a function which is say n minus 1 times differentiable. Right? If the function applied entry-wise preserves positivity for all positive matrices, and or I can even take rank less equals 2 positive matrices of a fixed dimension, then the function must have positive derivatives. F must be positive, F prime must be positive, F double prime, and so on. The first n derivatives which exist by assumption must be non-negative on the interval 0 to infinity. So that was one condition that was known from Horn's thesis, and in the spirit of Schoenberg and Rudin. So this result is by Loewner. Horn was his PhD student, and he cited this result of Loewner's. They proved it for continuous functions, and in the spirit of Rudin, we removed with Dominic Gio and Bala Rajaratnam, we removed that continuity. So you don't need to make any assumptions on the function. Well, so sorry, I should point out this was not there in the original setting, nor in our result. This is being put in for simplicity here. But the original setting had continuous functions. You don't need them to be continuous. So in particular, this does imply the Schoenberg-Rudin result for matrices with positive entries. So on the positive side, this condition is enough to prove that the function is a power series with positive coefficients. And just as a bit of history, so as I said, I was working in Stanford before this. So Loewner was a faculty there. So when he passed away, he gave all his papers to the library, and I went there and one day and asked for all those boxes and dug through them. And there is actually a letter in Loewner's own handwriting which mentions that he got interested in the following question: let f be a function defined in some interval. Consider all real symmetric matrices which are positive semidefinite with elements in this interval. Which properties must f have in order that the matrices are still positive semidefinite after applying the function entry-wise? And I found that if f is n minus 1 times differentiable, then the following conditions are required, necessary, and so on and so forth. So yeah, so this is Loewner's original letter to Josephine Mitchell, and this is the result that Horn cites. Okay, but he assumed he assumed here is differentiable, and then there was something about continuity which I'm skipping somewhere here. Anyway, so as a consequence now, as I said, I want to look at polynomials, and I want to find one polynomial with one negative coefficient which preserves positivity in dimension 3 or dimension n for a fixed n. So suppose n is such a polynomial, n is an integer. You have 2n plus 1 real numbers, say not all 0, none of them are 0. Look at this polynomial. There's n coefficients at the beginning, 1 in the middle, and n coefficients at the end. If this function preserves positivity in n by n matrices, then by considering f of x and Loewner's condition, f prime, f double prime are all non-negative, you get that these coefficients must all be positive, because that's what the first n derivatives that Loewner claimed. Right? Similarly, if you consider f of 1 over x and multiply by a power of x, then these would be the first few coefficients. So you would get that these last n coefficients must also be strictly positive, because I remember they are non-zero and now they are non-negative, so they are positive. So already, even if you have to find a polynomial with a negative coefficient that works in a fixed dimension, that coefficient cannot be among the first n and cannot be among the last n. It can only be, in this particular example, it can only be the one in between. And so you can ask, is this, which coefficients, can this be negative? And more generally, which coefficient can be negative? And this was not even known until 2017, let's say even. And this is a result that we proved then with Terence Dow, that there exists such a preserver with, you have to make the coefficient sufficiently small, but whatever, small and negative. But there exists such a preserver with a negative coefficient if and only if, whenever you have a negative coefficient, there are n coefficients before and n after which must both or all of them be positive. So I can have all these to be, this to be negative, these positive, one more negative coefficient, but then I must have n plus n further coefficients to be positive in a long power series of polynomials. So, and then we also sort of mention explicit bounds for how small that size of the negative coefficient is. So there are some quantitative bounds And those quantitative bounds can be made sharp in a restricted setting to this. But that's, as I said, that connects, all of this connects to Schur polynomials, to algebraic combinatorics, and I leave it for another day. And so the last part of the talk is we come back to the question I started with as a working example. When you have matrices with possibly zero patterns possibly, and you raise every entry of the matrix to some power, which powers preserve positivity? Okay? And that connects very naturally to graphs and to combinatorics. So far I've told you sort of I told you some basic definitions. I told you connections to metric geometry, how Schoenberg's results came up from positive definite functions on spheres, on Euclidean spheres. And then I previously told you Rudin's motivations from Hankel matrices, Toeplitz matrices, analysis even on locally compact abelian groups. The second connection was, and then there was a connection to sort of covariance estimation. And now let's finally get to, and something that I did not tell you about algebraic combinatorics and Schur polynomials. And now let me get to graphs. So again, this was motivated by applications. So in many applications, as I said, like the climate science example, you would find it rare for all variables to depend strongly on each other. And you actually rather sometimes even have domain-specific knowledge, like in graphical models, your structure of random variables is governed by a graph. And so you say that if two vertices are not joined by an edge, then they are independent or they're conditionally independent, and that is part of the model itself. So naturally there, you would want to work with matrices whose zero patterns reflect that model. And so this is how one does. One leverages this kind of independence to reduce the dimension. So here is a graph, the 4 cycle. There are 4 vertices. Corresponding to that, I have a 4x4 matrix. And now look at vertex 1 and 3 are not joined by an edge, so I put a 0. I constrain that entry to be 0. Similarly, 3, 1 is 0, and 2 and 4, 4 and 2. So this is how you encode dependencies in your model by a graph. Or you given a graph, you encode, or you talk about matrices with 0 patterns according to that graph. And so in the last part, as I said here, we will study matrices with zeros according to graphs. And so given a graph on n vertices, look at n by n positive semi-definite matrices. Entries, let's say in I, you can specify that. What you must also now constrain is how does the G come in? So n is the size of the vertex set. And now if you have 2 unequal vertices, which are not adjacent, then you must set that entry to be 0. And that's exactly what we do in the matrix above. So diagonal entries are allowed to be non-zero. And all these unconstrained entries are also allowed to be 0. They can be 0. But these 4 entries must be 0. They are not allowed to be anything else. And so you can, so here is how to constrain the matrices themselves. You can also constrain the functions. So let's constrain them to power maps. The only difference now is the power can be not integer. Remember, if you have any positive semi-definite matrix, then any monomial applied entry-wise preserves positivity. That's just the Schur product theorem and induction. So now I really want to understand which non-integer powers work in a fixed dimension. I fix the dimension, I fix the graphs, so the 0 structure. Which matrices preserve positivity there? And remember, so this was this example where I had the second example, non-path graph. And this is according to something called a banded graph. But anyway, so let's raise each entry to the alpha power. When is the resulting matrix positive? And this was a phase transition discovered by 2 students of Loewner. This is one was Roger Horn, as I said, the author of Horn and Johnson, matrix analysis. The other is Carl FitzGerald. They were both there at the same time at Stanford, but then this was 8 or 10 years after that, after their PhDs. X to the alpha preserves positivity on matrices with non-negative entries of dimension n, if and only if either alpha is an integer, that's just the Schur product theorem, or alpha is n minus 2 or bigger, any real number. So nothing, no non-real number before n minus 2, every non-integer number after n minus 2. So integer, 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 everything. So it's a very curious, kind of phase transition, if you will. So this is called the critical exponent in the matrix literature. And so, for example, in this above matrix, this is a 5 by 5 matrix. So every power bigger than 5 minus 2, every power bigger equals 3 will work. The question, of course, is can we do better? Can you improve on the 3 and make it less? In this case, of course, the answer is yes, you can do better. That's why I chose this matrix. So In fact, so this set n minus integers union this thing, this is really a finite arithmetic progression and a half line. And there are examples of this kind of a set in various other areas of mathematics. This is called the Wallach set, or the Gindikin-Wallach set, or the Berezin-Wallach set, or the Gindikin set. There are many people after whom it's named, depending on the area which you're studying. So in the representation theory, Nolan-Wallach was looking at some kind of holomorphic discrete series representations, and some unitarizability conditions led him to obtain this as the possible parameter values. And in complex complex analysis, complex geometry, so Verne and Rossi were looking at something similar for powers. I won't get into that, but they have this famous paper in ACTA in the 70s where they arrive at the same set, which they call the Wallach set. Gindikin was looking at something in probability in ensembles, and later on, in fact, in probability, in recent probability, in the central and non-central Wishart distribution studies, which parameters lead to the existence of such distributions? The answer is those parameters must lie in some kind of a Wallach set again. So this kind of a set has shown up in a bunch of places, but in fact it showed up in matrix theory. As I said, it showed up in matrix theory in 1977. It showed up in matrix theory 13 years before that. So when FitzGerald and Hahn were students at Stanford in the 1960s, in the very next building in the statistics department, Sam Karlin had discovered the same set of powers via total positivity. Okay, so maybe I will skip this in the interest of time. But what Karlin showed was that there is a certain Polya frequency function whose powers are totally positive or totally non-negative. If what Karlin showed is if alpha belongs to the exact same Wallach set node, then the powers of this thing are totally non-negative of order n. What about the powers below that? What about the non-integer powers below that? And that was somehow again not known since 1964. But in a recent paper, I answered the question that yes, no power below that is in fact totally non-negative. So the powers preserving total non-negativity of order n are precisely the same powers in 1964 discovered, which FitzGerald and Hahn rediscovered in a different positivity setting in 1977. So, and the remarkable thing is, they were sitting in the next building, but somehow this result was not known to FitzGerald and Hahn. You'd never see this result of Karlin in any of their papers. And I asked Roger Horn when I did this, and he did not know of this result. So it was very interesting. And the key ingredient for this is a paper of Tanvi Jain in 2020, in this February. I think she spoke at your colloquium a few months ago or last year or something. Anyway, so back to the problem at hand, and let me finish quickly. So remember, what were we doing? We started with a positive semi-definite. Well, we started with a fixed dimension. We started with a graph with n vertices. N is the dimension, and we want to understand which powers preserve positivity on matrices with zeros according to such a graph. So can we do better than the FitzGerald and Hahn crude bound by using these zero patterns here? And the answer is yes. In some cases, you can do so by exploiting the sparsity structure. So the problem now becomes, given a graph G, compute the set of powers preserving positivity on matrices with zeros according to G. And notice that such powers, if suppose G has 4 vertices, like that cycle graph I showed you, then every power bigger than 2 will work. Why? Because PG consists of 4 by 4 matrices. There are some extra zeros, but the matrices are 4 by 4 if G has 4 vertices. So by FitzGerald and Hahn's result, 4 minus 2, any power bigger than 2 will work. The question is really, can you do better? But in particular, there exists the smallest point, alpha naught, beyond which every power works. If nothing else, the alpha naught is the vertex at minus 2. Maybe it starts from earlier, but if nothing else, it is the vertex at minus 2. So really now one wants to ask, how do the set of powers preserving positivity on PG and this critical exponent, the smallest threshold value beyond which everything works, how do these two number and set, these quantities, depend on the geometry of the graph, on the combinatorics of the graph? Two special cases. So I should have pointed out what is, if you see here, right? So FitzGerald and Hahn studied the case when you don't have any constraint zeros. They said for all 4 by 4 matrices, powers bigger than 2 will work. What is the graph for which there are no constraint zeros? These are graphs where there are no missing edges, because missing edges give rise to constraint zeros. So these are precisely the complete graphs. So FitzGerald and Horn's result can be thought of as a special case of this problem for G, the complete graph. So FitzGerald and Horn studied the complete graph and proved that the critical exponent is r minus 2. That's exactly the result. In another paper with Bala Rajaratnam and Dominic Gio, we studied this case of trees, and trees are sort of easier to work out. We did many more things than just this result. But for trees, no matter what size, any power bigger than 1 works. So is it possible to understand this family for this critical exponent and the set of powers even more for some family of graphs which contain both complete graphs and trees? And so that's my last result here that I'll mention, and I'll mention some open problems then. So trees have no cycles of length anything, right? Any cycle bigger equals 3. There is a class of graphs called chordal graphs, and the idea is they just don't contain cycles of length 4 or more. So this is a non-chordal graph, because you see there's a red cycle here. The idea is if you see a cycle, draw a chord through it, and that makes it a chordal graph. So any graph which has already been triangulated, and then there may be some extra edges as well, is a chordal graph. And so here is the theorem. Let K be the almost complete graph on R nodes. So, sorry, KR1. So there's a 1 subscript, meaning I just take out 1 edge. Everything else, every other edge is drawn. Let this be the almost complete graph on R nodes. And then let R be the largest. So now, given a graph G, let R of G be the largest integer such that either the complete graph is contained in G or the complete graph missing 1 node is contained in G. Then, whenever G is chordal, you have exactly the same FitzGerald and Horn kind of theorem. The set of powers preserving positivity is a semi-infinite set and an arithmetic progression. And in particular, the critical exponent is r minus 2. And so this unifies all of these classes: complete graphs, trees, banded graphs, and so on. So in particular, this was a banded graph matrix. These zeros are according to a banded graph, for which you can now compute the critical exponent, and that turns out to be 2. So instead of the 3 that FitzGerald and Horn gave us, every power bigger than 2 will preserve positivity. Okay, before I tell you the last question, the point of this theorem is following. Right? Which powers preserve positivity? This is an analysis question. You look at some matrices, their eigenvalues are positive. You raise them to some powers, their determinants should be computed, or their eigenvalues, those should be positive. That's a completely analysis question. Inequalities. This theorem says if the pattern of zeros is according to a chordal graph, you can chuck the analysis out the window and just look at the graph, the combinatorics of the graph. See, this condition here has nothing about analysis. The combinatorics of the graph already tells you which powers preserve positivity. And that's the sort of remarkable connection to combinatorics, that you can really describe positivity preservers in terms of combinatorics. This was just for chordal graphs. What about for non-chordal graphs? For cycles, we have the same answer. The same combinatorial rule that I mentioned here will work when G is a cycle and you preserve powers preserve positivity on PG. For other non-chordal graphs, the answer is not. So it's completely open, and if you know a bit of MATLAB, you can simulate and really get intuition about this problem. You can even work just with correlation matrices. It's enough to preserve positivity on correlation matrices, or to not do so. And you can really just code and try to understand. There are even matrices, or 5 by 5 matrices, or graphs with 5 vertices, for which the critical exponent is not known. Anyway, so but that's a very natural question, and it's still completely open except for chordal graphs. The other natural question is, here's a strange looking, combinatorial graph invariant. So largest integer such that something happens. Is this graph invariant describable in terms of known graph invariants like the chromatic number or the tree width, or the degree, maximum degree, and so on? And we asked a bunch of people, even at Stanford, there were these Jacob Fox and Jan Vondrak and various other combinatorialists, and so far we haven't received any positive answer. So this looks to be like a new graph invariant, but one that naturally arises out of positivity considerations. And even it would be nice to answer this question: is there a known formula for this in terms of the other known graph invariants? Okay, so I'll end with the references then. So with Dominic and Bala, as I said, these are some of the places where we worked it out, including the critical exponents of graphs. That was really where we computed this for chordal graphs. And this was this paper was, so this is the survey article, and number 4 and number 7 was where we connected this thing to Schur polynomials. And let me mention number 8. This is actually a lecture notes for a course that I taught based on all these things and based on other topics in matrix positivity. And these are available on their website, but they contain sort of these complete proofs of Schoenberg's theorems on metric geometry, Schoenberg's theorem and Rudin's theorem on preservers. There's theorems on Polya frequency functions and their foundational results. And there are results about preserving positivity according to graphs. So all that with sort of complete proofs and very minimal prerequisites, preliminaries, are on my website. But yeah, so I think that's it for that. Thank you.
Okay, thank you. That was a wonderful talk. A lot of interesting things about different areas as well. So I'll throw open the floor to questions. If anyone has any questions, they can unmute their microphone and go ahead and ask. Meanwhile, I'll use my prerogative to ask a question. So a number of results you mentioned were of the kind where it was sufficient to consider matrices of a certain type. So either Toeplitz or Hankel.
Yes.
Lastly, you mentioned correlation matrices in any case. Is it easy to see, or can you say a little bit about why those kind of matrices are sufficient?
That's the hard question. That's exactly the hard question. So somehow they turn out to encode. So basically the idea is this, right? So how do you prove that something is some function is analytic, or as and then the preserved coefficients are non-negative, for instance. So you have to somehow conclude things about the derivatives of the function, and one way to do so. Yeah. So basically there are all these. So okay, so this thing about analytic with positive coefficients is what I described as absolutely monotonic functions.
Right.
These were studied in I think 1926 or even 1912, I forget, 1916, somewhere before 1930 for sure, by Sir Bernstein. And in this very long paper in ACTA, he developed the foundations of this thing, absolutely monotonic functions, even Bernstein polynomials, and so on. And so what it turns out is if your derivatives are all positive, then you turn out to be sort of real analytic, or then you turn out to be smooth, and then you have to do some kind of extra work to prove it's real analytic. And once it's real analytic, then you can prove that it's a power series of positive coefficients by just the identity theorem. Now, but how do you get that it's how do you get that it's absolutely monotonic? How do you get that it is smooth and its derivatives are positive? And that turns out to be a hard question. In fact, the sort of the black box underlying all of this that people use is a result of Ralph Boas Jr. and David Widder in 1940, which sort of says that if you have a function, no assumptions, except I think if you have a continuous function, and it has all its forward differences, there are no derivatives, there are no assumptions, but you can do forward differences and backward differences. If its forward equispace differences are positive, then the function is smooth and infinitely differentiable, and all those derivatives are positive at the origin and above the origin. So that turns out to be a result used, and that result of this is remarkable. It's a 6-page paper, I think, in Duke in 1940. It uses, I think, it uses 0 preliminaries. It uses 0 previous results. It literally, if you have studied one variable calculus, there are a sequence of 14 different lemmas, very clever arguments, and then they one by one, they pick off all the checklists and they finally get. And it's an incredible paper in that it proves so much, assuming so little. Just the forward differences being positive implies that the function is smooth of all sizes, of all orders, and all those derivatives are positive. And so really the point of using these structured matrices is how much is the minimum amount, what are the minimal set of determinant inequalities of preserving positivity, whether Hankel or Toeplitz or something like that, or rank at most 3 even, right? Which allow you to deduce that these forward differences are positive.
Right.
And so that somehow is what seems to go into all of this.
And that connection is quite non-trivial and not obvious.
That is the heart of both of our papers, both Rudin's paper and our paper, is to prove 2 implies 3 is the hard part.
I see. So you mentioned, the case of a hard cutoff was a function that preserved positivity.
Yes.
But is that only in a particular dimension? Because that doesn't seem like a smooth function. So
that's not a smooth function, exactly right. These are only in fixed dimension. And so in fact, So before I joined this thing, my collaborators, Dominic Gio and Bala Rajaratnam, they were working on this motivated by applications again. And so they proved that they in fact classified for which graphs, if you look at PG, where you constrain according to graphs, hard thresholding preserves positivity on PG for a graph G at some level. So you cut off at some cutoff, if and only if it preserves positivity on PG for every cutoff, if and only G is a tree. So in fact, even there, the result is somewhat negative, that hard thresholding really doesn't work on other graphs.
I see.
Only works on graphs with very sparse matrices, with zeros according to a tree.
I see. Has that got something to do with how, like in the compressed sensing world, you want some sort of independence of the columns? They have a specific phrase that they use, that these elements should not be connected too much in some way. Has that got something to do with that?
I actually don't think I'm sure about this. So I'll give it a pass. Sorry.
Okay. Okay. Are there any questions from the audience?
Hi Apoorva, this is Amit here. Hi. So one question, I guess not exactly, not quite related to positivity per se, but sorry, my mic got muted. These kind of structures that you mentioned, for example, thresholding and setting some entries to 0, or if you know of, let's say, a matrix which is coming from, say, graph, and hence you know some structure.
Right.
What is known about functions, not necessarily entry-wise applied, but matrix functions actually, so powers of matrices and so on, that preserve those structures then?
I don't really know much about that again either, but one thing I do know, for example, is so this thing about chordal graphs. If you go to chordal graphs, so and then you look at these, so the idea of Gaussian elimination. I just know literally one thing which I can tell you, which is that if you look at Gaussian elimination from some kind of from matrix, then you can of course you do all kinds of row and or some operations, row or column or both, right? Now, if your matrix has a structure of a graph, then when you do these row or column operations, certain zero entries might get replaced by non-zero entries, which would sort of be undesirable. You would be leaving the cone in which you are working.
Right.
But there's a characterization that says a graph, a G is a graph for which this kind of Gaussian elimination never disturbs the sparsity pattern, if and only if G is a chordal graph.
I see.
That is at least one application of chordal graphs in. You can safely do it without disturbing the zero patterns.
Right.
So,
do you have a reference for that? That sounds like a very interesting.
I don't even know reference. Maybe let's just search online probably.
Okay, cool.
I looked it up again many years ago. Dominic Gio actually showed it to me at some point. You will probably ask him, but
yeah.
I have a question. It might be naive, not well posed. So you talked about if I give you a graph and then you can ask about the kind of functions that will preserve the positive. What about the inverse thing? That is, I tell you that there is some function and it is preserving the positive definite. Can you put some statements about the kind of graphs or classify the kind of graphs?
That is very interesting. Naive things, obviously, yes. More substantially, I'm not sure myself. Actually, I've never thought about this question. That's a very nice question. Yeah, so I mean, so for example, if the graph shares a clique, right, then, so if the function is, suppose the function is not smooth, then that gives you a bound on the clique number of the graph itself. Because one knows that if a function preserves positivity on n by n matrices, so this thing that I told you about Loewner's result, if you don't know that the function preserves positivity on n by n matrices, that the function is Cn minus 1. So if I don't know this assumption, but I just know that the function preserves positivity, then I know this up to n minus 3. I know that the function is of class Cn minus 3. And the n minus third derivative is not just non-negative, it is also convex. So given this now, the contrapositive will give me some constraints on the graph. So suppose I know that my function is, let's say, C5, 5 times differentiable continuously, but not 6 times differentiable. Well, if it preserved positivity on 9 by 9 matrices, it would be C6. So it can't preserve positivity on 9 by 9 matrices, which means you just obtained some minors that you have to exclude from the graph. K9 can never be a minor of your graph. So certain things like that, maybe one can conclude, but otherwise, as I said, I haven't even thought about this question. I didn't. It's a very nice question.
Thanks.
Any other questions from the audience? I guess not. All right, if not, Apoorva, you will have to pretend we're all clapping very hard, and thank you so much for this wonderful talk. It was really interesting.
Thank you.